Okay, now we know the basic storage element latch, and SR latch was the basic. Then we modified and we introduced the control, and then we modified again so that we introduced an inverter and tied two inputs together so we avoid invalid states, and we introduced D latch. Then we have said that by using D latch one after the other, we have to introduce a inverter in the clock or the control input so that we won't have any transparency problem. One of them is updated while other one is sleeping. So master slave mode. This is what it's called. And by using this approach, by using this knowledge, now we can move into and we can introduce the clock into the game. Now, rather than using a control input, which is a level triggering, we can use clocks with the edge triggering. So this is a typical flip-flop, which we call it D-type flip-flop, and it's edge triggered D-type flip-flop. Now, what is important over here? We don't have control input, we just have a clock. And one of the latches, D latch, is the master, another one is the slave. So either two D latches or one D, one SR, it doesn't matter, it will give you the same functionality. And generally we are using two D latches as it's more simpler. Now what we need to take care, when this one is active, this will be inactive. That's why we call it master and slave. And this is what you can find inside of a typical D-type flip-flop, and it's edge triggered. Now, one thing that we need to understand is what is this edge triggering? Now, in the latches, we have seen that when control input is exactly 1, output follows input. That we called level triggering. And with the D-type flip-flop, when clock and Q plus, because it's changing based on that, when clock is 0, if it is a rising edge triggered, which is going from low to high, 0 to 1, we call it rising edge triggered or positive edge triggered. They are both accepted. On the lecture notes, it's written as positive edge. You can use it rising edge as it rises from 0 to 1. Now, what will happen when clock is 0? No matter what's happening, it just holds the previous value. So Q next is Q. Even clock is 1, Q next is Q. It's like a hold. Now, when it is going to change with the positive edge triggering, when the clock is changing from 0 to 1, whatever we have got in data D input, that will be reflected to the output. Output follows input. And if the clock is changing from high to low, then again, nothing will happen. So this positive edge triggered flip-flop only works with on the rising edge. You can also have negative edge triggered flip-flops. And with the negative edge triggered flip-flop, we also have the clock. We have got the Q next and negative edge. So low to high, high to low, sorry. So 1 to 0. Now when clock is 0, nothing will happen. When clock is 1, nothing will happen. On the rising edge, nothing will happen. But on the falling edge, now that means this is going to follow the data input. Okay, and that's known as negative edge triggered flip-flop. And the symbol for the flip-flops, positive edge, we have got a square, the input, clock, Q, and Q bar. Again, for the negative edge, it's opposite. We just have a bubble in front of the clock. It just means that the triggering works with the falling edge, okay, or negative edge. So that's the only difference, but we'll use the symbol a lot. So what we need to know, output Q next equals D on the rising edge or on the falling edge, but only on the edges. That's what we need to know. Okay, so if I carry on, negative edge, so this is slave, so the clock is inverted over there. So on the positive edge, as you can see, clock is inverted on the master, and this negative edge, clock is inverted in the slave. And this is what I explained, so high to low, then data. And there's a bubble in front of the clock. So if we carry on, we can also introduce enable. And that enable is introduced with the multiplexer. If you do remember multiplexer from the combinational circuits, when the select, in this case enable, is 1, we feed in data. Otherwise, we halt. So we can modify the symbol within enable. Now you can see that when enable is 0, it's still holding. When enable is 1, and on the rising edge, then output follows input. And another alternate one, which is a clock enable or clock gating. You can also use this if you want to have a low power design. You can switch off the memory elements by using a clock gating. But this is out of our scope of this course, so we don't consider that. Another inputs that we can use, asynchronous reset and set. So the input is working with the clock. Okay, so whenever the clock is changing, output is changing. But asynchronous set and reset, think about as a hard reset. Your computer is running, you just press the reset button and everything restarts. So that's how asynchronous reset and set is doing the work. And we can introduce these into the flip-flops as well. They are generally active low. So when they are 0, they are activating this asynchronous set and reset. So we can have, for example, asynchronous set and reset table. If we can draw it again. So we have got set, reset, clock, data input, Q plus, and Q plus inverse. Now what will happen with this? Let's say asynchronous ones first. S is 0, reset is 1. No matter what's happening with the clock and data input, then as these are active low, that means actually is set is activated, because maybe I can draw the symbol here. This looks like S, bubble, reset, bubble, active low. Then we have got clock, and we have got data input D, Q, and Q prime. That's how it looks like. So when S is 0, it means it's a hard set. So output will be 1, output inverse will be 0. Other way around, when reset is 0, it's hard reset. So this is going to be 0, this is going to be 1, no matter what's happening with the C and D inputs. And when both are 0, this is coming from the SR again. And as we don't care about these, it's undefined. Nothing will do a job over there. Now, when both inputs are 1, that means these are not active. So we have to wait for the clock. And on the rising edge of the clock, let's say is a positive edge triggered. If the input is 0, Q is 0, and Q bar is 1. Again, these are inactive on the rising edge. If the input is 1, Q is also 1, Q inverse is 0. So this is a typical application of asynchronous set and reset with the functionalities that you have seen. Now, we have seen the first flip-flop, which is a D-type flip-flop. if we summarize it, this is the basic and the most simplest flip-flop that you are going to see. Because why is it simple? Q next is just D. So on the rising edge of the flop or on the falling edge of the flop, output follows input. This is what we call it. Output follows input. And the symbol that we need to know is D, clock, Q, and Q bar. Okay. Now, as we have gained this knowledge, let's use this D-type flip-flop and let's start doing some sequential circuit analysis in order to check if we have given with a circuit, can we analyze it? Okay, so these are all what we have done, so I'm just skipping them quickly. You can check it from the lecture notes. The behavior of sequential circuits can be characterized in terms of flip-flop input equations. So if we have D-type flip-flop, we have to find the input equations, and from that we can derive the next state equations because we know the input equations that goes into the flip-flop, and then we can understand what we are expecting as a next state equation and also the output equations. So here is the first example. Now, two D-type flip-flops are given. Some combinational circuits are over there. We have got outputs and we have got some feedback paths and input X. Now, how are we going to analyze a circuitry? We can go specifically by flip-flop by flip-flop. So let's start with flip-flop A. What do we know about flip-flop A? There's a combinational circuit. We can easily write what DA is going to be, right? Because that output of combinational circuit is fitting into the input of flip-flop A. So I'm saying DA. Now we have got X feeding in and QA. X, QA is the present state showing over here. Then X and QB. So or X QB. This is the equation for DA. And then let's do the same thing for flip-flop B. And we need to find the equation for DB. This is what? This is coming from QA inverse. And it is X. So this is flip-flop B. Now, as we have got two of those inputs, and there's this one output, which is Y, we need to find an equation for that as well. Output Y. And this is X prime. So Y is X prime. And this is what? This is coming from QA and QB. So QA plus QB. Now everything is written in the form of Q's and A's. We can actually simplify this, I mean, as a way that writing it. So dA can be AX plus BX. I'm just getting rid of these Q's because we know that they're all Q's, present state. So dB, it's going to be A prime X, and Y is going to be X prime A plus B. Now, input equations. These are input equations. This is step one. Now then, we have to derive next state equations. So how do we derive next state equations while we are analyzing? So deriving a next state equation, we have to know the next state equation for the D-type flip-flop. What do we know? Q next equals D. So whatever we have got on DA is actually going to be QA plus. So let's say I want to have a next state equation, which is going to be dA, which is going to be AX plus BX, as we have found it over here. Then B plus, it's going to be dB, and this is going to be A prime X. And Y is written as it is, X prime, as there are no flip-flops, is just A plus B. So now, this is step 2. We have got the next state equations. Okay, the first 2 steps of analysis are done. The next analysis step is state table. Now, we know our equations, so I'll just rewrite them. A next state is AX plus BX. B next state is A prime X, and Y is X prime A plus B. So these are our next state equations. In order to derive the state table, this is the simplest way of doing this. Present state input, next state, and output. Now the present state are A and B's over here. So I have got 2 flip-flops. So that means I have to have A and B. Input is X. Next state is A plus and B plus. This is what we are going to find out, and Y. Then so present state and the inputs are they're all inputs. Next states and the outputs are outputs. So 3 inputs, 0, 0, 0, 8 possible combinations. One zero zero, 101, 110, 111. All right then, let's start with A plus. So how are we going to derive A plus table? It's so simple. We just need to replace the values over here. So A is going to be 1 when A is 1 and X is 1, or B is 1 and X is 1. So A is 1, X is 1, A is 1, X is 1, A is 1, X is 1. So at these 2 points, A is going to be 1, or when B is 1, X is 1. So B is 1, X is 1, and B is 1, X is 1 in the last one. The other ones are all zeros based on this equation. Then the next state equation for B is A prime X. That means when A is, let's change the color, when A is 0 and X is 1. A is 0, X is 1, A is 0, X is 1. So at these 2 points, B plus is going to be 1, and the rest are all zeros. And Y is what? Either X prime, this is like, let's just put in it the way. This is A, X prime, or BX prime, which means that when A is 1, X is 0, and when B is 1, X is 0. So A is 1, X is 0, this is 1. A is 1, X is 0, this is also 1. When B is 1, X is 0, is this 1. And B is 1, X is 0, it's also this one, which is already covered. So the rest are just zeros. And that's the state table that we can use in our analysis. So if I go further with the slides as well, next state equations, the state table. So we derive the same state table. You can also have a different type of state table, which we call it 2D state table. So you can write the present state, next state when x is 0, x is 1, output when x is 0, x is 1, rather than having a separate column for x. This is also possible. Which one is more suitable for you, you can use that. Now, at this point, I want to give you a important info about these sequential circuits, which generally they ask in the job interviews if you are applying for an electronic engineering or logic design engineer or something like that. We have got two types of models, Mealy and Moore. Now, what are they? Mealy and Moore models. Mealy and Moore models are when we consider the circuitries, if the outputs at any instant of any instant depends on the state, the circuit is referred to as Moore model. So if the output is only dependent on the states, the circuit is a Moore model. And in Moore machines, inputs directly influence the next states. So you can see that from here. Okay. And the combinational logic. But in Mealy, as you can see, input is directly affecting the output. In Moore, inputs are not affecting the output, but in Mealy, inputs are affecting the output. So this is something important. This is something that we need to understand. So if we go back to the circuitry that we have got, is this Mealy or Moore based on the output given over here? Let's look at it. Is X affecting the output? As you can see, X is an element of that output equation. So we can say that this is a Mealy model. It is affecting, and yes, it is a Mealy model because of X. States are there, input is there, so it's a Mealy model. Now, when we talk about these circuitries, the last step of analysis is the state diagrams. So, state diagram. Now, how do we get this state diagram? I'm just going to go back to the table that we have got. Based from the table. So, first step was next state equations. Second step is a state table, and the third step is state diagram in circuit analysis. So how do we derive state diagram? Now, how many states do we have? For present state A, we have got 0, 0, 0, 1, 1, 0, 1, 1. So two flip-flops can be in 4 possible states. So let's write them down. In the state diagrams, we use 0, 0, 0, 1, 1, 0, 1, 1. And they are normally written inside of the bubble. These are representing the states. Then we look for the conditions. So for example, when we are in state 0, 0, If the input is 0, we wait in 0, 0. So I can say that when I'm here, input is 0, I wait there. And the output is also 0. Now, as this is a Mealy machine, and as the output is changing based on X and the present state, I have to write my output next to my input. So that means that's also going to be 0. Then, present state is 0, 0, input is 1. Next state is 0, 1. So from here, when input is 1, I have to jump to 0, 1. The output is 0. Then, present state is 0, 1, input is 0, I go back to 0, 0. So when input is 0, I go back to 0, 0, and the output is 1. So I wrote output next to it. When I'm in 0, 1, if the input is 1, I jump to 1, 1. So 0, 1, if the input is 1, I jump to 1, 1, and the output is 0. When we are in 1, 0, if the input is 0, I go back to 0, 0. So 1, 0, input is 0, I go back to 0, 0, and the output is 1. 1, 0, input is 1, I stay at 1, 0, and the output is also 0. And 1, 1, input is 0, it goes back to 0, 0, and the output is 1. And 1, 1, input is 1, it goes to 1, 0, and the output is 0. So that's the state diagram of this circuitry, and we are completed the analysis. So in the question, when I ask you to analyze a sequential circuitry, first you have to derive the input equations and the next state equations. Then you have to derive the state table. And then finally, you have to derive the state diagram. Okay, so we can do one more example where the input equations are given for this circuitry. We have got XORs in the diagram, as you can see. So X, Y are two inputs, and we have got Z as an output and one flip-flop. Okay, so input equation is dA. It's the feedback A XOR X XOR Y. And Z is just A. That's it. So A plus, which is the next state, is going to be A XOR X XOR Y. Nothing else. And Z is A. That's all you need to know for step 1. Then we can derive the state table. So with the state table, we have got present state A, we have got input XY, we have got next A plus, and output Z. So 3 inputs, once again 8 possibilities. And for each of those, we will derive the next state values and the output. Okay, so A XOR X XOR Y. What do we know? It's an odd function. If we have odd number of ones, then output will be 1. So 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 1, 1, 1 is 0, 1, 0, 0 is 1, 1, 0, 1 is 0, 1, 1, 0 is 0, and 1, 1, 1, it's 1. So odd number of ones are giving output as 1. And then Z is A, so whatever we have got on A, it will be reflected to the output. Now, the question is this a Mealy or Moore model? It is a Moore model because Z is just an output of the present state, the flip-flop. So X or Y is not affecting, they are not in the equation. So we can say that this is a Moore model. Then, state diagram. Now, I can go through over here as well so that we can see these states. We have got two states, present state for 0 and 1. So that means I have to have two states. I'm drawing them bigger because in the Mealy, we were writing the outputs next to our inputs. In the Moore model, we have to write our outputs next to our states. So present state 0, output is 0. Present state is 1, output is 1. And they are written next to each other. Now, the conditions. Input x, y. When both are 0, next state is 0. 0, 1, next state is 1. 1, 0, next state is 1. 1, 1, next state is 0, 0. Then, when we are in present state 1, inputs are 0, 0, we stay. 0, 1, we stay. With 0, 1, it goes back to 0, sorry. 1, 0 goes back to 0. 1, 1 stays. And this is the state diagram of our circuitry. And we are done with the analysis of this circuitry as well. You can draw the 2D state table. That's also acceptable. State diagrams, they are the graphical represents information in the state table. And they're easier to derive directly from logic diagrams and their equations. And we have to use them in the analysis of sequential circuits. And two states, as you can see, when both are 0, next state is 0. 0, 1, next state is 1. 1, 0, next state is still 1. And 1, 1, we stay at 0. When we're in present state 1, if the inputs are 0, 0, we hold in 1. 0, 1, we jump back to 0. 1, 0 also jumps back to 0. And 1, 1, it holds at the same state. So this is how we can use next state equations, tables, and state diagrams in order to analyze it. So we already drawn the state diagram for the other circuitry, and this is also repeated over here as well. When both inputs, when the present state is 0, input is 0, we stay, same as what we have done. When it is 1, it jumps to 0, 1. No matter what way you write them, they're all acceptable. There's no strict rule for that. We jump to 0, 1. When we're in 0, 1, if the input is 0, we go back and output is 1. When the input is 1, it jumps to 1, 1 and output is 0. 1, 0, if the input is 0, then it goes to 0, 0 and output is 1. 1, 0, if the input is 1, it stays where it is. 1, 1, input is 0, it goes back to 0, 0, output is 1, and 1, 1, input is 1, it goes to 1, 0, and output is 0. So this is how we do the analysis of this circuitry. One another thing that we can identify in these state tables or state diagrams, maybe we can optimize this circuitry. How do we optimize the circuitry? We can look at if there are similar states. What do we mean by similar states? When you look at the table, if the present state, input, next state, and the outputs are matching, we can get rid of those. We don't need to repeat the same states. So when you look at the table, over here, now we have to make sure that they're all matching. So for example, 1, 0 state in both cases, 0, 1, 1, 1 state, 0, 1. Now, when input is 0, next state is 0, 0. When input is 0, next state is 0, 0. So far is good. And the output is 1, output is 1. Now, when the input is 1, next state is 1, 0, output is 0. When the input is 1, next state is 1, 0, output is 0. So we can easily see that these two are identical when you look at it. They are equivalent to each other. So what we can do is we can get rid of one of those. Okay? So if we get rid of 1, 0 state, now at this point where we are jumping to 1, 0, we will jump to 1, 1. So 1, 0s are going to be replaced with 1, 1 because 1, 0 is not going to be there anymore. As you can see, our state diagram reduced. We just have 1, 1, and whenever we want to jump to 1, 0, we jump to 1, 1. Okay? So at this point, this was 1, 0. Okay? So this was 1, 0, now it is 1, 1. Okay? 1, 0 now becomes 1, 1. That's replaced. Then, if we look at it again, is there any other similar ones? So, as you can see, 0, 1, 0, 0, 0, 1, 1, 1, state 0, 0, 0, 1. So, the first condition satisfies. Then, when input is 1, next state is 1, 1, output is 0. Input is 1, next state is 1, 1, output is 0. So, these are also matching. So, we can see that they are similar. I get rid of 1, 1 state. So, when I get rid of 1, 1 state, whenever I call 1, 1, I have to go to 0, 1. Okay, so as you can see, now two states left. And this is more optimized compared to this one. Now, as two states have left, you don't need two flip-flops anymore. So we can actually optimize the circuitry, and we can just use one flip-flop, and that will implement the function that's required. Okay, so we can see that we can optimize also the sequential circuits by identifying the equivalent states and getting rid of them.